This is a question in which two lenses are involved, one convex lens and one concave lens. So let us first see the question. So the question says, consider a system of two thin lenses the convex lens has a focal length of 20 centimeters and the concave lens has a focal length of minus 10 centimeters. So this is according to the sign convention that we have seen before. So from the sign convention, the convex lens would have a focal length having positive value and concave lens would have a focal length having negative value. The two lenses are separated by 8 centimeters, so they are not placed in contact with each other. There is some separation between them. For an object of height 1 centimeter which is placed at a distance of 40 centimeter from the convex lens, calculate the position and the size of the image. So let us first draw the diagram before attempting to solve this. So we have a convex lens followed by a concave lens. The separation between them is 8 centimeter. This is the principal axis. So the focal length of the convex lens is 20 centimeters. So somewhere over here, this distance being 20 centimeter, and the focal length of the concave lens is, let's say, somewhere over here. This being 10 centimeter, and the object is placed at 40 centimeters. So somewhere over here, this is our object. An object is not point sized, it is height 1 centimeter. So this is our object, and this distance right here is 40 centimeter, and this height of the object is 1 centimeter. So this completes the diagram. We could also draw the focal length of the convex lens somewhere over here. This could also be focal distance of the convex lens. Similarly, for the concave lens, we can have it somewhere over here. But when we consider the principal focus, then the principal focus for the convex lens is after the lens. So this is what we will consider for the convex lens. And similarly for the concave lens, it is before the lens. So this is the principal focus for the concave lens, because we typically assume that rays would be coming from left to right. So this is the diagram that we have. We need to find out the image and the size of the object which is placed over here. So let us start solving the question. So in the question we have two lenses. First the convex lens and second the concave lens. So the rays start from here and they meet the convex lens first. So according to the sign convention, the rays are moving in this direction. So this direction is positive, this direction is negative. And the rays encounter first the convex lens, then they will move and encounter the concave lens, and then the image will be formed somewhere. So let us start by first looking at the convex lens, but before that, the formula that we are going to use is the thin lens formula. Thin lens formula, which we have seen many times before in this video series. So this is our thin lens formula. We will use it twice, first for the convex lens, then for the concave lens. So first for the convex lens, we will have by using the sign convention and plugging in the values, we have focal length is 20 centimeter and object distance will be negative according to the sign convention. So this is so we found out the image distance from the convex lens, which is 40 centimeters. So the image for the convex lens is formed somewhere over here. So this distance is 40 centimeter. And then we need to find out the magnification. So magnification is given as V over U. This is the formula for magnification. So in this case, we have V is 40 centimeters, U is minus 40 centimeters. So magnification for the convex This means that the image has the same size but it is inverted. So this location was our V convex, and image is of the same size but inverted. So this height right here is 1 centimeter, but it is inverted. Now let us consider the case for the concave lens. Now for the concave lens, this image formed by the convex lens acts as the virtual object. So for the concave lens, the image of the convex lens acts as the virtual object. So let me write it down. And if we draw some rays over here, so let me draw one ray over here. So we'll have, let's say, a parallel ray coming in, hitting the convex lens, then it will get converged and then hit the concave lens, and then it will be a little bit diverged because of the concave lens. But since we considered just the action of the convex lens first, so this ray will this parallel ray that is coming from there, from the top of the object, will be, let's say, focused over there had the concave lens not been there. Similarly, I think I should redraw this diagram once, otherwise it will get pretty much cluttered. Let us redraw this diagram. So if we have a lens passing through the center of the convex lens or the pole of the lens, then it would move undeviated and would essentially meet this point had the concave lens not been there. So this point, this basically image from the convex lens acts as the virtual object for the concave lens. So we have this distance right here from the object to the pole of the concave lens would be the object distance. So that is going to be 40 centimeters minus 8 centimeters. 8 centimeters is this separation, so it is 40 centimeters from here. Subtract the 8 centimeters, then you would get this distance. This is our object distance. So this is 32 centimeters. Focal length of the concave lens is given as minus 10 centimeters. So let us put it in the thin lens formula. plugging in the values. This gives us plugging this value in the calculator gives us approximately equal to 14 sorry minus approximately equal to minus 14.5 centimeters. So if we go back to our diagram, our image distance is minus 14.5 centimeters. So this is from the concave lens. So somewhere over here. So image is formed somewhere over here. This distance is 14.5 centimeters, approximately equal to 14.5 centimeters. And now we need to find out the height of the image. So magnification so this is minus 14.5 centimeters divided by 32 centimeters. Again, putting this in the calculator would give us approximately 0.45. This is approximate value when putting it in the calculator. So we find out the magnification as well. Sorry, there's a negative sign out here. Now the image from the convex lens, magnification of the convex lens was -1. This means that image is going to be inverted, and height of the image same as 1 centimeters, because magnitude is 1, just inversion is happening, and we had the object height as 1 centimeter. Over here another inversion is happening because of the negative sign. Another inversion. This is because of negative sign. So height of image is going to be approximately equal to 0.45 centimeters, because it was 1 centimeter to start with, and then this magnification factor would be multiplied. So this gives us 0.45. So height of the image is going to be roughly over here, roughly 0.45 centimeters. So if we draw the diagram once again, the final diagram sorry about this. Let me paste it in a new page. So this is the final diagram that we have. Let us erase some unnecessary stuff. This will add to the clarity of the diagram. So this is where our image is. This is image location, and height of the image is roughly 0.45 centimeters, and it is erect. This was F concave for us. So finally we solved this question, and the result is image. For the image we have erect image of height approximately 0.45 centimeters, and it is approximately minus 14 point, or we can just write approximately 14.5 centimeters before the concave lens. And since the separation between concave lens and convex lens is 8 centimeters, we have that the image is located roughly 6.5 centimeters before the convex lens. So this solves the question. We were supposed to find out the position of the image and the height or magnification of the image. So we find this is height or magnification, and this is position for the image that we formed, given that the object is placed over here of height 1 centimeter, 40 centimeters away from the convex lens is the object, and then we find out that the image is roughly 6.5 centimeters away from the convex lens. So this concludes the question.